Okay, so in the interest of time, we'll go ahead and kick off as folks are continuing to come in. So good morning, everyone. And I would like to welcome you to the second webinar in our 2021 Spring Science Seminar Series. It's brought to you by the Southeast Climate Adaptation Science Center. My name is Carrie Furness, and I'm the program manager here at the Southeast CASC. And in this virtual seminar series, we're highlighting CASC projects that support resource management actions across the Southeast. So if you'll advance the slide, here's what to expect from today's webinar. So first we'll go over some meeting logistics, including getting some feedback from you just by a short poll. And then we'll introduce our speaker for the day. He'll present for about 40 minutes or so, and then we'll have plenty of time for Q&A and discussion at the end before we wrap up. So now I'll pass the mic over to Ashlyn Shore, our communication specialist at the CASC, who'll give us a quick intro to our Zoom interface.
Thanks, Carrie, and good morning, everyone. Thank you so much for joining us this morning. I'll quickly, as Carrie mentioned, just go over some of the features of the Zoom interface that we're using for today's webinar. So as noted on the slide here, these controls on the bottom left of your Zoom screen will allow you to connect to audio using either your computer or the phone number listed here, or here rather. So this is also where you can mute and unmute your audio down here in the left corner. And then just a quick note for those who may be joining us only by phone, *6 is the code to mute or unmute your phone. So throughout the presentation, we will just keep all lines muted, and we ask that you also keep your video off just so we can lessen the amount of distractions during the presentation. So in the middle of the bottom bar of your Zoom screen, you can access the chat window. And I'd encourage you, if some questions come up throughout the presentation, just go ahead and submit them in the chat for discussion. And our speaker will answer those during the Q&A session at the very end of the talk. So we will be recording today's webinar, and you can access and share that recording afterwards from the Southeast CASC website, our Science Series webpage, and our YouTube channel. And finally, if you want to be notified of upcoming seminars or other events, please just add your email in the chat, and I'll make sure to get you subscribed to our monthly newsletter. So that's all from me. So I'll pass it back to you, Carrie.
Ashlyn. So now I'd like to launch a short poll, just 2 questions, just to get a bit of information about who's with us today, and also to help us know how to continue to let folks know about this these webinar series, which we find to be very helpful and a great opportunity to interact with our resource management community and other science communities. So, all right, great. Looks like those are rolling in. So I'll just another second. Looks like we've got equally university and federal agencies and some other folks joining us. Nice. Okay, I'll go ahead and end this and share the results, and appreciate your giving us that information. That might help our speaker too know sort of who's on the line and how he might, target information. So moving on from that here, we'll go on to our presentation. So I'm pleased to introduce Dr. Adam Terando. So Adam is a research ecologist with the U.S. Geological Survey here at the Southeast Climate Adaptation Science Center, located at North Carolina State University. So he's also adjunct faculty in the Department of Applied Ecology. He's a climate scientist by training, and his research focuses on the risks posed by climate and land use change to ecosystems and the complex human-environment relationships that drive these processes. This includes understanding climatically induced changes to fire in the Southeast, simulating suburban growth patterns, and developing ultra-high resolution climate projections for the U.S. Caribbean. He has served as the federal coordinating lead author for the Southeast chapter of the recently issued 4th National Climate Assessment, and as a co-author on the North Carolina Climate Science Report. The title of his talk today is Using Information from Global Climate Models to Inform Policymaking and Natural Resource Decision-Making. It's a part of what he'll be discussing is a USGS report that he authored along with some other USGS colleagues with the and the application of some of that information to policy and management decisions. So we'll share the link to that publication later in the presentation in case you'd like to delve a little deeper into that. So now we'll pass it on to Adam and take it away.
Great. Thanks, Carrie. All right. Let's go ahead and get started. Okay, so thanks again for the introduction and happy to be here. So I just wanted to start off just first really quick, just what I sort of do here. And I'm not going to go into any detail on these because I don't have time for that, but just to give you a sense of the types of things that I work on. So that spans the gamut from climate change risks and fire adaptive ecosystems to coupled natural human systems modeling. That's the simulating urban growth that Carrie mentioned, that those ultra high resolution projections that we talked about, that was for this, what we call end-to-end climate change adaptation science for the US Caribbean, helping managers adapt to climate change as it affects vulnerable and threatened species. And then actually what I'm going to talk about today is sort of the scientific assessment and advising that I've been more and more involved in the past couple of years as it relates to things like the National Climate Assessment, or as you'll see today, helping decision makers and policymakers better understand how, what the purpose of climate models is when we're using them, not strictly as research tools and to help us better understand the world and the universe, but to actually help to decision makers make better decisions and inform policy. And so thinking about that in terms of, again, my overall philosophy, and I think a lot of what we do in the CASC network, we can think of climate change as this one big applied problem, really, this applied science problem, in that scientists, in general, we're figuring out what is climate change, what sort of climate, when is climate change happening? What are the characteristics of climate change? What could we expect to happen into the future with climate change? And then what are the consequences of climate change? That's a lot where the CASC network steps in, and a lot of other, my colleagues in USGS thinking about and across our university partners, like what does this mean for different ecosystems, different species? And that ultimately then we can think about that in the big picture though. We've been thinking about that in terms of like, should we then undertake the big decision as to should we reduce the amount of carbon that we're emitting into the atmosphere? So that's like a risk management decision. There's consequences of climate change. How do we manage the risk that is accrues or that we can expect given that? Where we usually do most of our work though is in this bottom one on the adaptation side. So there's consequences of climate change, and that informs the big decision, the decision as to should we reduce global greenhouse gas emissions. But then there's the multitude of decisions that happen on the ground that regardless of what we do in terms of global policy to reduce emissions, how are we going to adapt to the climate change that's already occurring or the climate change we can expect in the future? So dealing with climate change is really a risk management question, and that's a lot of what we at the Climate Adaptation Science Centers, the type of science we bring to bear. So as a preamble to the report that I'm talking about today, there were some questions that started coming up mainly in the last administration. And the types of questions that we were getting and that were percolating either from the top of USGS or from the top of the Department of Interior were things like, can we trust climate model predictions? And I put those in scare quotes for a reason, as you'll see later. Should we use climate model results based on the highest emission scenarios to still inform decision making, or are those no longer, plausible at all? And are long-term climate model projections useful to Department of Interior? What's the foreseeable future, to use a term in a certain act that we all pay attention to, the Endangered Species Act? So these were the types of questions that we were getting, and we were tasked then with addressing those and clarifying, what USGS what sort of the science, the overall science says about these from the international scientific community, and what's the role of the USGS and applying the information, using the information from climate models in particular to help inform policymaking. So that was this report that we published last year with my colleagues, who you can see here. Some of them are involved in or part of the CASC network as well. And we wrote this very short report. I think it's like 25 pages, something like that. And tried to really just use really clear, concise language to address some of these questions. Today, I'm really just going to be focusing on the first two parts of these. But if you're interested, please check out the publication. Again, it's not a 200-page or 400-page, doorstop. It's really short and I think clearly written, and so hopefully you'll find it of use. So overall, the context and sort of the major thesis we were operating under, again, as I mentioned before, is that climate change is really a risk management problem. And so those risks, how you deal with that risk is then you have to think about it in terms of what's the context of the decision you're making. Okay, so what are the stakes involved is one way to think about it. On the left, here's a hypothetical example. So what you would do, the risk you face with climate change is going to be different if you're talking about, say, sea level rise or affecting a boardwalk in a wildlife refuge or a park, like here in Assateague Island National Seashore. What a decision maker might do and how they feel about the risks they're facing with climate change might be different in the context on the left versus the context on the right when you're talking about a species that might go extinct under climate change. So thinking about like the utility of the climate science and how you might use climate model results is going to differ under those different contexts. But overall, one thing we tried to establish in the report was what is the need for climate science and climate impact science in the federal government as it applies specifically to natural resource management. And again, this sort of thinks about like, the federal government has a responsibility to manage these resources. Sometimes it's to manage, sometimes it's to protect, sometimes it's to prevent, say, again, things like endangered species from going extinct. And so the federal government has a duty and an obligation to plan for the future so that we can make wise decisions and manage the public resources wisely and make sure we're meeting our obligations for trust species and trust systems. This is something that we do a lot in the federal government. And in particular, thinking about like, that question in terms of like, why would we, like, is it even like responsible for the federal government to be using climate model projections that go out 80 or 100 years in the future? Well, again, yes, but it depends on the context of the decision you're making. This is an example I like to use. This is from my old professors at University of Delaware who took part in this. This was a decision or an assessment that was undertaken, funded by the Department of Energy way back in the early 90s, where they wanted to know what is the climate risk based on placing the nuclear waste depository in Yucca Mountain. So what sort of like flood events could occur over the long time period, because of course there's a very long half-life when you're talking about radioactive waste. And so what is the risk of such a repository being affected by a flood, a really damaging flood event? So they got these climate scientists together, and of course they didn't really have, at this point 30 years ago, they didn't have like the same computing power we have now. So they had to use more of an expert opinion in terms of what they think the next 10,000 years might look like for the climate and for in particular precipitation and temperature in this area. But they were able to do that. So in this case, the stakes were high, and they wanted to know over the lifespan of which they were concerned, in this case 10,000 years, what might the climate look like here? So the government has this history of looking very far forward in the future, or looking as far into the future as is necessary given the decision context and the risk that you're trying to assess. Okay, so before we go further, just a few definitions here. These are things that are going to come up a lot in the talk. So, and there's really three things I just want to mention: scenario, projection, and prediction. We like to differentiate between those three things when we're talking about climate models and how we use them in decision making. So, scenario is just a sequence of events that defines a plausible future. One way to think about it is a scenario is when you have the question is what if? So what if the future unfolded in this manner? A projection is a predicted outcome for a given scenario of the future. So what do we expect or what do we predict would happen if the future unfolded in a particular way? And then finally, prediction, that's sort of the strongest case we're talking about here. A prediction is a statement about the future expressed with some degree of certainty or likelihood. So what do we expect or what do we predict the high temperature will be tomorrow, okay? And those have in distinct and nuanced differences, those definitions, and they're important to differentiate between those when we talk about this. Okay, so why do we use scenarios when we talk about using climate models to inform decision making? Well, scenarios are really useful when we're dealing with decision contexts with high complexity and or high uncertainty. Okay, so predictions, scientists want to be able to make predictions. That's like the best case scenarios. We want to be able to draw upon our knowledge and build models so that we can predict what would happen in the future given some external stimuli or given the march of time. But sometimes that's really very difficult to do. Okay, when you're dealing with high uncertainty, deep uncertainty, or systems that are very complex, or more likely the case both, then lots of times it's just not really possible to incorporate all of that uncertainty and complexity, all the myriad ways that those things can interact in nonlinear ways. And therefore, you need to move into that less stringent type of thinking about the future, which is a what if type of situation. So again, now you're thinking about what if, not predicting with any kind of certainty what will happen. So this leads us to climate scenarios. Okay, so climate scenarios where we start off. Now, that doesn't mean we don't have any sense of what the future may hold. It just means we relax the standard in terms of how much the degree of certainty we're going to be looking into the future. I'll talk about that more in a minute. With climate scenarios, it's sort of a three-step process. You start with greenhouse gas emissions. Okay, so certain pathways or trajectories of greenhouse gases, whether it's carbon dioxide, methane, those sorts of things, the most prominent greenhouse gas emissions. We use fairly simple models to then translate those emissions into how those would translate into equivalent, say, carbon dioxide concentrations in the atmosphere, okay, or other greenhouse gases. But lots of times we use carbon dioxide and just sort of translate everything into a common one common measure of greenhouse gases. And then we use that to then inform the climate models. Those provide what we call the boundary conditions and the forcing scenario for the climate model. So we run the climate models. The climate models take that information. They say, okay, if the greenhouse gases are this level through time, then how might the climate respond? And so using these climate scenarios, and when you combine those with climate models, that helps us to better characterize and hopefully manage risk, because we have a much better sense of, under this uncertain and complex future, we still have more certainty about what the future holds than under this way of dealing with uncertainty. So in this case, each scenario then represents a set of assumptions about future greenhouse gas concentration. That becomes really important. That's where that scenario aspect of this, that what if aspect of scenario building and using climate models comes into play. One term that we used more, and we see more used in the literature, is we talk about plausibility of scenarios instead of likelihood. And what we're really talking about is a plausible range of trajectories. Okay, so this is, you'll see this in the most recent IPCC assessment, which the new one's going to be coming out pretty shortly. But the most recent one, which we call the 5th assessment report for the Intergovernmental Panel on Climate Change, IPCC, we have this range of scenarios. And you see here on the y-axis here, this is annual carbon emissions, ranging from a high emission, very high emission scenario to a scenario where we humans take pretty dramatic actions to reduce the amount of emissions in the atmosphere now and into the future. And so plausibility in this case, so although we're not saying that there's a likelihood for any, we're really loath to, or hesitant to try to assign a likelihood to any particular scenario, we do have a standard of thinking that this range of scenarios should define our plausible range of future outcomes, okay? And it's not an exhaustive list of future outcomes, but it is a plausible set of scenarios. And so plausibility in this case is defined by physical and socioeconomic constraints defined broadly. So things like how much retrievable carbon actually is there in the ground? How much carbon can we dig up, and how fast could humans actually dig it up? What are plausible demographic pathways for the future? And how fast, you know, if you're talking about a mitigation scenario, maybe one option for mitigation is actually sucking carbon dioxide out of the sky. So how fast and how feasible is that as an option? And so because we are typically interested in scenarios that represent futures where the climate is forced to respond to some, you know, change in the climate system, change in the energy balance, this is just sort of an aside for a definition. We refer to these scenarios lots of times as forcing scenarios. So if this is another definitional slide, if you hear me talking about a forcing scenario, that just means a climate scenario, but we're sort of forcing the climate to respond to some external change in the energy balance of the climate system. So it's being forced to respond to that. And so, for example, again, in the last assessment, Intergovernmental Panel on Climate Change assessment report, we had what were called these RCP scenarios. Okay, and so RCP stands for Representative Concentration Pathway. So for example, the Representative Concentration Pathway, or RCP 8.5, represents a future where the net change in radiative forcing, again, the energy balance, at the Earth's surface by the year 2100 is increased by 8.5 watts per meter squared. Okay, so I mentioned this already, but with this plausible range of trajectories, we use a plausibility standard instead of a likelihood standard because it's really difficult to say which scenarios are more likely. You know, at this point, the temptation might be to say, and I hear this a lot, you know, RCP 8.5 is unlikely because it's at the very high upper end of the range of the scenarios. But this implies that other scenarios are therefore more likely, right? And that there is a most likely scenario. How would we go about determining that? That's sort of the tricky part. You know, for instance, if you think about like, is global mitigation of future greenhouse gas emissions, is that more likely? Is that where we're thinking there's a right skewed distribution? How would we determine that that's more likely? Or is business as usual more likely? Are we thinking there's more likely outcomes that we're going to keep emitting, increasing the rate of carbon dioxide emissions like we have in the recent past? You know, and then of course the temptation is to say, well, why don't we just split the difference and look down at the middle? You know, that's sort of what we do lots of times. We say when we take a mean of different samples from a population. In this case, that's not really helpful though, and it could be misleading. There's just randomly taking the middle, you know, across all these scenarios. That's really sort of an indeterminate prediction. There's not really, this is not a Gaussian distribution of outcomes. And that also, again, thinking back to the complexity of scenarios, this high complexity, you know, this could represent, say, a situation where there's no mitigation, no greenhouse gas mitigation, and low GDP growth. Or it could be, say, there is strong mitigation measures, strong actions to reduce greenhouse gas emissions, but there's still, say, a high GDP. across the world, or something else. It's really hard to say that if you're saying, well, this is a more likely scenario, it's hard to really say with certainty what that scenario actually is. So what we settled on in the report, and which is still sort of the best practice in the scientific community, is that for timeframes of decades or longer, the best unbiased practice is to assume something closer to a uniform distribution. So each scenario we say is plausible, there's no central tendency, and it's up to decision makers to decide which are useful to consider based on their own risk tolerance. In my experience, this is not really something that decision makers like, but it's something that is still just really being having the closest fidelity to what the science allows us to do at this point. Eventually, there is hope. Eventually, we can rule out scenarios as implausible as we move through time, because obviously some of these scenarios will no longer be plausible because they just don't match the observations, or as policies are enacted that foreclose the possibility of certain pathways. So if, for instance, under the Paris Agreement, if you're familiar with that, if all the countries in the world adopted that, and not only adopted the Paris Accords, the Paris Agreement, but then enshrined into law the actions that would make the goals of the Paris Agreement much more likely to happen, we could probably then rule out something like RCP 8.5 as no longer being plausible. But until that's the case, or until we move through time and we're able to, the observations show that this or that scenario is no longer plausible, it's best practice really just to look across the entire range as being our plausible outcomes for the future. Okay, so this brings up another question though, is like, why might a decision maker consider an extreme, quote unquote, extreme scenario, either extremely high or extremely low? Let's focus on extremely high. So an RCP 8.5. Well, one reason is to avoid overconfident decision making. So here's an example. This shaded area, this is in the report, we overlaid the range of scenarios that were used in the very first IPCC assessment report issued back in 1990. Okay, so this was the range of scenarios that were considered. The black line is the observed emissions through time up to 2019, I believe. So if you can see here that observed emissions have actually been at the extreme high end of the plausible range that was considered in that first report from 1990. So in this case, if decision makers had sort of implicitly disregarded the high trajectory, the highest scenario of emissions, they would have been setting themselves up to not really fully considering the risk that they were actually facing at the time. Given deep uncertainty and high complexity about the future, if they had said, well, that's the high-end case and we're just going to disregard that, they would have been setting themselves up potentially for going under a course of decision-making that would have set them up for more damages, more loss. And one could argue that that's actually what has happened. So that's one reason to avoid overconfident decision making. Another reason to consider different scenarios and maybe even these extreme scenarios is to actually influence the future outcomes. If you have control over the future, say if you are the head of a world government that releases a lot of greenhouse gas emissions, you might want to consider the extreme scenario. In fact, this is why we do this, because then you might say, well, the consequences of scenario X at this extreme end are unacceptable. The damages are too high, the losses are too great. Therefore, we are going to enact policies and take actions more in line that would get us more on a scenario Y or trajectory Y, okay? That's really the entire reason for doing things like these scenarios in the IPCC assessment, to get societies and governments to come up with things like the Paris Agreement to say that this dangerous anthropogenic climate change is unacceptable. And so we're going to then take actions to avoid that. The final reason you might do this is to buffer against potential damages. This is be a situation where you don't have control over which scenario you will go under into the future, or that you will travel along the future. And so therefore you have to mitigate damages if you don't want something to happen in the future. If you're trying to avoid losses or a certain type of damage, you're going to examine, well, what might happen under this extreme scenario? And so then what actions could I take to avoid losses should that scenario come to pass? Okay, so those are the scenarios. Those are helpful for understanding the overall climate in terms of the greenhouse gas in the future. But to actually understand the climate response, we need to use climate models. So what are climate models? All right, well, climate models are numerical models. They're a little bit different than, say, the empirical models or the statistical models that we use a lot in biology or ecology. The closest analog to climate models are things we use for our weather forecasts. So the atmosphere and the ocean, they can be modeled as fluids using basic fundamental Newtonian physics. So the motions of the atmosphere and the oceans and the energy exchange within and between those systems and through external forcings are mathematically explained. They're not statistically explained, they're mathematically explained. Climate models, the way we then take that information from our understanding of physics and chemistry, is we code those up in computer models. Okay, so climate models represent our understanding of how the climate system works written in computer code. Here's an example of an actual computer code from a climate model. And lots of times, because these are really computationally intense, we have to run these on supercomputers such as the Titan supercomputer shown here. The original climate models, they were simple, they were atmosphere only, did not have many processes that they were simulating, and they had very coarse resolution. Say on a hemispheric scale, you could have one number for, say, an entire hemisphere, or maybe more like 10 numbers for an entire hemisphere. And you had several levels in the atmosphere. That's what's shown here on the left. This is an example from model temperature by latitude and height for one hemisphere, published in 1965. So since these models only simulated the general circulation of the atmosphere, the ocean was not considered explicitly at this point. The term GCM, which probably a lot of you have heard, originally meant general circulation model. As GCMs got more complex, the acronym evolved to mean global climate model, and now we talk more and more about Earth system models, or ESM, because we're adding more and more processes. So the trend over time is to add complexity as computing power increases and as our understanding of the climate system improves. So what do climate models do well? Well, simulation of global and continental climate patterns, subcontinental patterns, particularly for things like mean temperature, atmospheric circulation, and representation of most large-scale climate drivers within the system. Things like El Nino that we think about as having a large influence on climate variability from year to year. There's things that are still very challenging for climate models to simulate. In a word, clouds. Clouds are very difficult and an ongoing challenge, and ongoing improvements are made to our simulation of clouds. But also, it's difficult to simulate well regional and local climates because the models, this is more just a computational problem. The models just are not set up to do that. So here's an example from Puerto Rico where the you can see here, this is an example climate model mesh grid that you would see over the island. So climate models still have pretty coarse grid cell resolution, we say, because again, it's just so computationally intensive to run these 3D models, 4D models really. So you would have one number for this entire grid cell here, representing whatever climate variables you're interested in. So we can't really use climate models to resolve these local climates or climates with complex topography, and we have to use other methods to do that. Okay, so how are GCMs, though, at the global scale used to inform decision making? Well, GCMs are used to project how the climate could respond to perturbations of the system as defined for the different scenarios. So those perturbations are what I called forcings before. This is really an important distinction from weather models. So these are both numerical models. They operate under the same principles. But weather models, the goal is to actually predict, not project, but predict the actual observed weather, the exact condition of the atmosphere at some point in the future. Global climate models are not trying to forecast the weather for decades into the future. They are not trying to predict, say, what the high temperature is going to be in Raleigh on March 16th in 2072. Instead, we construct experiments where we use multiple climate models to simulate weather conditions that are representative of how the climate could respond to some external change applied to the system. So GCM experiments help us understand how the character of the weather, again, the character of the weather, and thus the climate, because climate is the average of weather over time, could change given a particular plausible scenario of the future. So if you have a plausible scenario, you can use climate models to predict how the climate would respond to that scenario, which we then use to project a climate response into the future. All right, so here's how this works on a granular level, just so you have a little window into the guts of how we do these climate model experiments. So climate modelers, they start with what we call a control run. This is a long model simulation, typically 500 to 1,000 model years. So you have to start some model spin up, where you start the model cold, like starting a car engine up cold, and you allow the model to spin up all the systems that you're simulating in the climate system, so then they come to some sort of equilibrium. After spin up, the simulated global mean temperature, which is what we're using for our proxy for the overall climate system, it's simulating all the different key variables of the climate system, but we are focusing on mean climate temperature here. It fluctuates naturally from interactions among the climate system components. So the control run stabilizes us around some mean state plus variability, if you want to think about this in a statistical sense. At this point, no change in the external forcing or the change in the energy balance is applied. Once it's stabilized, again, after that 500 or 1,000 model years, the instantaneous climate state, which is the model's simulated values for the atmosphere, the ocean, the biosphere, or whatever, every 20 years or so, is used as initial conditions as if it's some past year. Okay, so let's say, if we want to start our climate model experiment and say the year 1850, because that represents the last period before humans really started influencing the climate system in a strong way, then we're going to just start to pick different points along our control run to say, all right, we're going to take this year and we're going to use that as our start year for our pre-climate warming year. And now we're going to apply our new forcings, the forcings that are what have been actually observed over the past. So the new forcings that are applied represent the historical and observed changes in the atmospheric composition of greenhouse gases, plus things like volcanic eruptions and changes in solar output. All those forcings that can affect the Earth's energy balance and affect the Earth's climate. Okay, so a big advance in setting things up like this came with the advent of what we call the CMIPS, or the Coupled Model Intercomparison Project. This was an effort that was started in the 90s, where participating modeling groups agreed to perform a predetermined set of climate model experiments. And this allowed open access to terabytes of climate model results from around the world, so the entire scientific community can use these. And this then creates an ensemble of climate model output, okay? So now we take all those different climate models where we've run the control runs and we've started the climate model experiments looking across the point in time when humans really started adding greenhouse gases to the atmosphere. And then we see if we want to go forward in the future, we bring all those model results together into an ensemble of climate model output. This is really advantageous because an ensemble of models permits much better characterization of uncertainty about future change, since the models performing the same experiment can be analyzed together, okay? So this helps us capture uncertainty better. And there's going to be that uncertainty due to the quasi-random sequence of natural variability. So that's things like, Again, picking those different points in the control run, you might just pick one model year that represents 1850. Well, maybe there was, in that model year that's representing 1850, there was a very strong El Nino year. Maybe in another model year that represents 1850 to start the experiment, there was a strong La Nina year. That's going to then affect going forward the sequence of the sequence of natural variability, which can then affect those short-term trends. And so it's important to have this ensemble of climate model results to capture that type of uncertainty, as well as the scientific uncertainty we have about how strongly the climate system will respond to rising greenhouse gases. Okay, so we've done all that. We take our control runs. We start at different points along the control run, provide the climate model, the forcing conditions, both for the past, and now we run the experiment over the past and into the future with our different forcing scenarios. These are then our climate model projections. They project how the climate would respond to a given forcing scenario. So since each climate scenario is considered to be a plausible outcome, we will refer to the experimental results from our climate model experiments under these different scenarios as climate model projections, okay? That's why we distinguish between climate model projections versus true model predictions or forecasts like our weather forecasts. So notably though, GCMs, they offer no special insight as to which scenario is more likely. Okay, so here we're looking at, say, the global average temperature change at the end of the 21st century under our low emission scenario, RCP 2.6, compared to our high emission scenario, RCP 8.5. So this means we don't know what path humanity will take with respect to future greenhouse gas emissions. We covered that already. So GCMs, climate models will not help us in that regard, knowing what actions humanity is going to take in the future. Okay, so just going to just a little bit more depth here and in terms of uncertainty in these climate scenarios. The reason we're doing that is because understanding this uncertainty helps us understand the types of risk that we face. So there's three primary sources of uncertainty, and I've already alluded to some of these. And the importance really depends then on the time frame of the projections, and of course then the time frame of the decision that we're trying to make. So uncertainty about future climates in the first decade or two, when you're projecting into the future, is really driven mostly by these large-scale multi-year weather patterns, things like El Nino, La Nina, the North Atlantic Oscillation, Pacific Decadal Oscillation. You might have heard of some of these terms. And so that's this internal variability. This little figure here, which comes from a famous paper by Hawkins and Sutton several years ago, it's disaggregating different sources of uncertainty into three different types: internal variability, scientific uncertainty, and scenario uncertainty. And which type of uncertainty accounts for the amount of total uncertainty we would expect at different points in time if you're looking in the future. So for that first decade or two, most of the uncertainty is driven by this internal variability of the climate system. As you move into about 20 to 50 years out, the uncertainty then is primarily driven by our unresolved scientific questions about how the climate system works. How sensitive is the climate to adding gigatons of carbon to the atmosphere every single year, which is what we're doing. So in a sense, humans are performing this grand experiment, which we'll only really find out the answer to as we move through time. But our climate models are our best guess, our best representation of what we know about how the climate system will respond to that. But there's still uncertainty. We haven't figured that out completely. After you get beyond about 50 years from the start of your experiment, this would be roughly about 2055 based on the last IPCC assessment report. For the next one, that'll be about 2065. The range of uncertainty is driven mostly by human actions that affect global greenhouse gas emissions. So now the uncertainty is mainly driven by, well, are humans going to take actions to reduce greenhouse gas emissions or not? So when we're thinking then about climate models, skillful climate models, when we're trying to assess their utility for looking at projections in the future, skillful climate models should be able to reproduce climate averages and trends over the past as long as they had the correct boundary conditions. There's no expectation for a skillful climate model to reproduce short-term climate fluctuations. So this is sort of combining what we're talking about with the short-term climate variability and, say, the forcing scenarios. So for instance, here's looking at climate model results. Those are the gray lines here over the past. And this brown thick line would be the observed, okay? So in 1991, you would expect global climate models to be able to simulate that short-term effect on climate because that's a forcing that was included in the climate model experiment, okay? We told the climate models in 1991 there's a large volcanic eruption, and that's a change in the energy balance because we wanted to be able to provide the GCMs with that type of information. The climate models should not, skillful climate models would not be expected to simulate, say, the really strong warm event in 1998, except by chance, because that was mainly due to a very strong El Nino that occurred that year. That's unforced climate variability. That's just the random sequencing or quasi-random sequencing of internal variability that is going to be different for each climate model. And there's only one realized sequence of that natural variability that the Earth will undergo. And we don't expect climate models to be able to align perfectly with that. Okay, so we're wrapping up here. Thinking about the best practices for climate model projections and impact analyses. These were our recommendations in the report. One thing we really tried to stress was that for these recommendations, the scientist really needs to use their own best judgment when using this information. So we caveat this by, when feasible and appropriate, use a wide range of scenarios. Use multiple climate models, and to best assess future risks, consider climate relevant timescales, including things that are 100 years or longer, depending on the decision context, and thinking about delayed impacts, say from sea level rise. It might be, depending on the decision context, you might want to examine sea level rise projections 100, 500, or 1,000 years in the future, depending on what sort of decision you have to make. So these are the types of best practices that we recommend. And of course, try to articulate the uncertainties the best you can and how they're expected to evolve over time. So, overall, dealing with risk and uncertainty is difficult because there is no objective answer. Lots of times, I get asked like, well, which scenarios should we use? Which one's going to happen? Which one's most likely? And it's just really difficult to answer that. But that doesn't mean that you can't make a decision if you're a decision maker. It just means that decision makers probably have to do the work to assess their own levels of tolerance for risk and loss, and how amenable they are to say taking an action that's under a certain assumption about what the future will hold, and then being wrong about that, okay? And I know decision makers don't like to make decisions where it turns out they were wrong about what the future would hold, but I think you can let the scientists take the heat for that. And as long as decision makers are just clear about what their own risk tolerances is and try to be transparent about that. So this is showing some of that when we think about maybe trying to do this in a more formalized way. On the right-hand side is just these, looking at these different types of risk, a decision maker who might be risk averse on this utility function versus risk neutral versus risk tolerant. This is sort of the more canonical or neoclassical view of this, versus now thinking about this sort of asymmetric loss aversion, getting into more behavioral economics, thinking about how people are more likely to view gains versus losses. And there's no right way necessarily to view this. It's just that everybody has their own tolerance for risk and loss. And it's probably best to just be transparent about that. And that will help us make wiser decisions when we're using this sort of information. And finally, then, when in doubt, ask us, ask the CASC network. We're here to help. And, so with that, I will gladly take any questions. Thanks for your time. All right, Carrie, I think your mic is off. I don't hear you. I think you're talking. can't hear you, Carrie. I know your mic is off, but there's no audio coming.
Here, I'm switching to my.
There you go.
Yeah. So sorry, I thought that was nicely articulated, a lot of information, but we'll go ahead and get quickly to the questions. And it looks like they're coming in the chat window. Adam, if you would like to read that out from Mike, make sure it gets into the audio record. I appreciate it.
Yeah, well, I guess Mike's going to start off with, continuing this argument we had. So Mike Runge says, for a decision maker to use the full suite of risk analysis tools, namely expected utility theory, to assess their risk tolerance, they need scientists to provide probabilistic predictions of the future. How can decision makers proceed if the scenarios are not described probabilistically? Well, the way I tried to get around that, Mike, was to say, let's assume it's a uniform distribution. Okay. So yeah, it's not, a likelihood like, say, that we're used to thinking about in terms of a Gaussian type of distribution or whatever distribution you want, but sort of heuristically, you have to just assume that each scenario is equally plausible or likely. So if you're only considering, and so then it becomes a matter of truncating your scenarios to the set under consideration, and then you just have to assign equal weight to all those scenarios. So that's how I would say we have to go about do that. There's not going to be a elegant, say, completely elegant solution, but I think when we're dealing with this in the real world, that's how you have to go about doing it. I feel better doing that than trying to say RCP 6.0 is the most likely scenario into the future.
So if I could follow up, Adam, yeah, that makes sense. But what you just did was you did turn them into, you basically take the uniform distribution across the scenarios.
Yeah.
And you now have provided a probabilistic prediction
Right.
because now you can weight those 4 scenarios in a uniform way, which is great because then you can do all the stuff that a risk analysis and a sort of activity theory. I guess the only question I'd press a little bit further is, well, okay, if you're going to put weight on those 4 scenarios or 6 scenarios or many scenarios, equal weight, sure, great starting point. What if you consult economists, political scientists, and they say, well, we're thinking about what governments will do. We think the middle 2 scenarios have, a total of 80% weight, and the 2 extreme scenarios should have 10% weight. I mean, like, you could take it a step further to try to consider all 4 scenarios, but not have equal weight by bringing in other information about, I like that graph that you showed of splitting out the scientific uncertainty from the scenario uncertainty from the internal uncertainty. Why not grapple with the scenario uncertainty and try to and try to do the best job you can of maybe bringing in, maybe the climate scientists don't want to make those judgments, but maybe others would. Anyway,
and some people have wanted to, but I would say what I'm operating under, and I think what in terms of the USGS wide enterprise, I guess, is operating under is where the scientific community writ large stands when it comes to this, when it comes to the set of scenarios that are used in the IPCC, the assessment report. For individual contexts, yeah, you have much more freedom and much more flexibility on the approaches you use. And maybe you do want to just do that, and if the decision makers are comfortable with that, by all means. But in terms of, say, trying to come up with best practices and standards across, multitudes and multitudes of decisions, I think a starting point, maybe this is my own personal risk tolerance, I'm starting from a more conservative approach in terms of, let's start with what the scientific community has agreed upon for now, which is more of an equally plausible standard rather than trying to assign weights to individual scenarios.
And I guess I'm just you're arguing it from the standpoint of the scientific enterprise. I'm arguing it from the standpoint of the decision maker's enterprise, which is to say, the decision maker could say, you haven't provided me enough. I need more information about the likelihood of those scenarios in order to make my decision. So
and sometimes that's feasible and sometimes it's not, right? And sometimes you have, because again, who are the decision makers from the IPCC scenarios? It's the entire world, governments, and they have decided to work with that set of scenarios. And again, they're operating under more of a, I guess, depending on the decision maker, under a, are they operating under a risk aversion type of approach, or what sort of tolerance are they operating under? So anyway, all right, Mike and I will get here later and talk about this more. Okay, so Charlie says, I think I'll ask you to describe the ensemble of global climate models. If all outcomes are equally plausible, what is the benefit of a collection of ensemble models, if not to estimate the probabilities of outcome? Just struggling to understand how I should interpret the suite of results provided by the ensembles. Okay, well, yeah, this is, again, we have these philosophical discussions in the climate science community, and there's different statistical interpretations of what an ensemble actually is, and again, in practice, sometimes we do sort of look at these as sort of like within a scenario. Maybe you do interpret the ensemble of results within a scenario as a sample. And so then you are interpreting these probabilistically. Okay, so then you're thinking about the ensemble as truth plus error. But there's another way to look at it, which is sort of like that these are sort of exchangeable futures, and they're not just picking random balls out of a bucket, but they're sort of like just equally plausible results of how the future can unfold, because they're not samples of the climate. They're just our depictions of the climate in the future. That's not really a great explanation, Charlie, but I guess what I'm saying is that within a scenario, it is common to look at these probabilistically, but there's still some nuances that some people feel uncomfortable with. So I don't know, we can talk more about that offline. I feel a little bit more comfortable doing that on the ensemble end than I do on the scenario end. Okay, so Alyssa asked a question. Hi, Adam. What do you think is the best approach for selecting GCMs when modeling the impacts of climate extremes? Well, the first thing is to try to use as many climate models as possible rather than picking them, unless they're just completely unskillful, like they're just not, they just are bad models, for lack of a better term. So there are ways you can do that, to think about, like, you just have to set up your sort of test, some people call it a model bake-off. You have to set up your test sort of smartly so that you're actually assessing the skill of a model, rather than giving yourself a sense that you're assessing skill, but you're really not, or you have you're an unreliable estimate of model skill. So there are ways to do that. You just have to be really careful in how you do it. Okay, so we said, John says, risk analysis and which scenarios you pay attention to is very much dependent on the decision context. If the potential outcome is the end of civilization or the loss of 1 million species, you probably want to pay more attention to RCP 8.5 than 2.6. Absolutely, totally correct. And so that's part of the point I wanted to make to Mike. So that's a really good point to bring up. Thanks for that. All right. Any other questions? Okay, April had a question. She did direct message. I think she meant this for everyone. Many land use changes are made at a local level. How does this report and other future climate research get integrated into where decisions are made? Well, that's lots of times that's a whole other talk called where we talk about how do we step down those global climate results to a local level if you're thinking about, say, precipitation extremes. And there's this whole enterprise called downscaling, and we've given other talks on that, where that's the way that we do that to be able to better incorporate climate model results into that local scale that you're talking about. So again, that's a whole other type of question, April, but maybe Carrie can let us know if there's other recorded talks where we've talked about that before. I know that we've given many, many talks on that subject before. All right, Tom says, I heard of an online resource on the radio that would make downscaled GCM projections available for locations globally. Is there such a resource, and can I look up climate projections for my house? Yeah, there's many tools out there. I don't have them memorized off the top of my head. If anyone else wants to chime in, I don't know if Carrie or if Ryan Boyles is on the call. Someone can chime in on that. There are, there's as many downscaling approaches as there are climate models to downscale. So sometimes you have to be careful about what you're using it for. Again, if the stakes are just, oh, I wonder what the temperature is projected for my house and the climate in 50 years, then maybe the stakes are low. But if the stakes are high, like you're using it to say, inform policy at the local or state level or draft a new law, then you probably want to consult some experts and make sure that you're using an appropriate approach to do that. Okay, yep, thanks for those links. Those are good links to use. And okay, any other questions? I know we're running up to lunchtime here, at least on the East Coast.
Yeah, thanks, Adam. This is really a great presentation, and some good questions. And so if there's follow-up, I just want to encourage you to reach out to me, to Ashlyn, and we'll connect you with Adam or other resources. But I think take to heart the idea that if you need help with climate modeling, get in touch with the CASC. So we can definitely set you up with information that you might need and interpretation as well. So given that we are just past the top of the hour, we'll turn it over to Ashlyn to just wrap up real quickly with just a presentation of indication of what's happening in our next seminar. So thanks all for joining.
Yeah, thanks, Carrie. And really quick, I don't want to go too far into anyone's lunch hour, but did just want to let everybody know about the next presentation in our spring seminar series. It's going to be held on April 20th at 11 a.m. Eastern Time. That presentation is going to be given by USGS research ecologist James Cronin on the topic of strategic habitat conservation for the brown pelican, estimating habitat objectives and management scenario efficiencies. So we hope that you'll register and plan to join us for that discussion. I'm quickly just going to include our newsletter subscription link where you guys can get updated on the announcement for that and the registration link. So thanks everyone for tuning in and joining us today, and thanks Adam for that great presentation. I hope everyone enjoys the rest of their Tuesday, and please continue to stay safe.
Thanks everyone. Take care.
Thanks all.